First, I want to thank the organizers, including Ray. I've never been to this conference. It's nice to have a sunny place in the winter, although it's getting sunny in Alaska now. Also, I want to thank Jeff for his excellent introduction, because I'm talking about his point 6 on the list of future work, okay? That is to say, time-dependent domains. Now, I'm not assuming, let's see if I can get this right, there we go. I'm not assuming that you know what a nonlinear complementarity problem is, so I want to give a quick introduction to that, and it's okay, the rest of the outline will appear when I need it. Because we're used to solving nonlinear equations, okay? And I want to talk about constrained nonlinear equations, which I claim the mass conservation problem for a glacier or an ice sheet or sea ice has a constraint that if you think of these things as having a thickness, they have a positive thickness. So that's the punchline of the talk, and you can go home, but the rest of it is the details, I guess. So if you haven't seen one of these things before, that's what that really is a definition of a nonlinear, an NCP. I have a hard time saying it. The obstacle problem is a good one to think about weak formulations, and it's also representative of what I'm doing, and I can draw it in 1D. So here goes. Famous obstacle problem, you have a fixed obstacle, that's the blue, and then you have you want a membrane, or in this case a string, to drape over it. And that is to say, where you're solving a PDE, a differential equation anyway, where the gap is positive here, and you get a straight line. But where it's in contact with the obstacle, you aren't solving a PDE, you're solving something else. And this is one of the forms in which to think about that. And if you think about the gap in particular, where there's a gap, where there's a gap, the gap is positive. And in that case, the concavity of the gap is exactly equal to the concavity, because you're solving that, of the obstacle. Whereas where it's in contact, the concavity should be one-sided. That is to say, this formulation gives you just switch hands because I'm shake less. What you see here is this complementarity. That is to say, either the quantity you're solving for is 0, or the equations you're trying to solve are 0. That is to say, this, and otherwise they're always one-sided. Now, it would be fair to say, isn't there another formulation of that? In fact, I prefer this formulation, except when I'm trying to explain things to glaciologists, and actually both are really useful formulations. So it's actually easier to say the obstacle problem, and I'll try to suggest how the glacier problem works as well. It's easier to say the obstacle problem. The obstacle generates a convex and closed set of admissible functions, and you want to solve these equations, but you don't quite solve these equations. Instead, you solve that inequality. Okay, so those are some examples, maybe to give you a picture of what I'm talking about when I'm talking about these NCPs and VIs. And I'm going to say NCP and VI a lot because they're equivalent in the context I'm talking about. And in fact, the software is written frequently by people who are confused about whether they want to even call them VIs or NCPs. So you get papers about NCPs, which then the software objects are called VIs and so on. So anyway, you go back and forth between them is just fine. Both of these formulations are sort of a way of weakening the nonlinear equations we intend to subject to a constraint. A comment, this is very relevant to the mass conservation problems. Glaciers are one of them, but all these mass conservation problems don't come from optimization. So there have been talks this morning, in fact, about variational inequalities and obstacle problems, and my obstacle problem was an optimization, but the glacier problem was not. So I can look at a VI and NCP formulation, but it won't come from a symmetric Jacobian or Hessian. Okay? And before I move on to actual glaciers, I just want to say I used the components that are fairly new in Petsy SNES with Barry Smith's help to make them work. I think there's some support for these kinds of problems in other places. A colleague, Guillaume Gervais, and he's now at ETH in Zurich, has used Dune, but I went looking, I'm not sure it's still maintained. Anyway, the Petsy form can be used through Phoenix and through FireDrake. So I've seen talks about using that technology if you're interested. And within that Petsy SNES, world. They're called SNES-VI, but they're NCP methods. Anyway, there is a semi-smooth method. I guess I'm not going to say anything more about it. It's something I can avoid spending time on. I used this one, and it was quite successful. And the basic idea is when you're away from the constraint, you do things. Ironically, that's called the inactive set. The active set's where you're up against the constraint at a certain Newton step. But if you're away from the constraint, then you basically compute a Newton step and then do a line search, but the line search has a little bit of additional information about the constraint. Okay? So, glaciers. The problem I'm going to talk about is this time-dependent domain. So there are two unknowns. I'm going to ignore energy, so there's no temperature unknowns. There are other possible, more elaborate problems, but my problems will have two unknown fields, the ice thickness and the ice velocity. I'll switch back and forth between the thickness h and the surface elevation. They're both equivalent sort of descriptions of the unknown. The bed is data, and the surface mass balance, that is to say whether it's snowing or melting, is data. Of course, it's not data. And in fact, what we're really interested in as ice sheet modelers, everybody's interested in this, is what's the degree of uncertainty coming from our models if we pretend these things are data. The one I'm going to focus on is bed elevation, but there's just as much uncertainties to care about with surface mass balance. However, the problems I'm talking about are much less sensitive to the roughness. The solves are very sensitive here to the bed and rather insensitive to the surface mass balance. So if it came from a bunch of data and it has a bunch of roughness in it, it doesn't really matter. So I want to solve these two problems coupled together. Now, I do recognize that incompressibility is usually thought of as a mass conservation thing, but I'm talking about an incompressible fluid layer. And when you model incompressible fluid layers, you treat incompressibility straightforwardly. Everybody does it by vertically integrating to get the vertical velocity, and usually the vertical velocity goes away. So I'm going to do that, and once you do that, you sort of tend to see one equation with a time derivative in it and a Stokes problem, or a simplified Stokes problem with no time derivatives in it. So maybe I'm misnaming this, but it doesn't really matter. I'll move on from that. Oh, I want better ice sheet models than the one I'm working on. That was what those little things were saying. This momentum solver, which I'm saying basically from now on is going to be an abstract bunch of symbols, it's a black box. It takes in geometry and produces a velocity field, exactly what Jeff was just talking about. And it could be as fancy as Stokes, or it could be as simple as the shallow ice approximation, or it could be something in between. And there's a fair amount of literature now on numerical and sort of asymptotic arguments as well for this sort of hierarchy of models. But having said that, this equation is one people treat as trivial, and I'm saying is not trivial. In fact, I think it's all the difficulty in terms of the roughness of the problem. I think Eisman-Palm did a disservice to the community saying that there was sort of the roughness has to do with this distinction in the hierarchy, and I think actually roughness has to do with how solvable is this equation, how far forward in time you can move. Anyway, we'll get off my high horse here. This is a problem that applies to a lot of objects. That is to say, a fluid layer in a climate. I emphasize the climate because if this term over here is non-negative, for instance, then it's completely different. It's easy. You just make sure that your transport scheme, however you handle this, has a maximum principle or properties like that. But if you have a sign term, then the constraint that the thickness is positive is really active, okay? That is to say, if you can kill off the layer by A, then you have a free boundary and you have to pay attention to its presence and you have to enforce the constraint. And glaciers are one of those, sea ice is another. Tidewater marshes where evaporation is controlling the shape, or groundwater absorption. And I put this up as a counterexample. It's actually not something where anybody's tsunami model is ever going to have evaporation or groundwater absorption in it. So no, it's actually not an example. But then there's a long list of other examples in addition to these, which I'm confident in, and subglacial hydrology is one of them where you have a thin layer and an active constraint to enforce. So I'm going to semi-discretize, but I'm not doing method of lines. I'm doing the other method of lines. That is to say, instead of lines this way, I'm lines this way. Note there's in this coupled model, there's only one time derivative, so I just discretized it. But this now is a continuous space problem. The momentum solved, however we do it, generates a u from our geometry. That's where the bed comes in, but it goes into that term and it controls the difficulty of solving this problem for the updated geometry, okay? And my point, to give away the punchline again, is that we need to weakly pose that strong form up there. And I mean not just multiply by something and integrate, but actually incorporate the constraint. So one way, and the way that has a very short literature, this is pretty much the summary of it, is to use variational inequalities. Fine, I'm moving on. The equivalent once you discretize, so it's something I really want to get to this point down here, is to write down an NCP. That means the equations you're going to solve are the residual f. F means the residual here, just like it does when you're doing Newton's method. So our NCP is like this, and when the thickness is positive, you're solving the usual mass conservation equation, no different. That is to say, you have your residual and you need to get it to be 0 there. But in an open set where the thickness is 0, and this applies to the converged problem, in a thickness in an open set where the thickness is 0, what this is saying is something actually useful. It is that the surface mass balance, that is to say the climate, was sufficiently melting, negative, so as to remove the last ice sheet, okay? So that is to say, that's what you get from a glaciologist's point of view, is that ought to be part of the same problem that is involved in updating the geometry of the glacier. You ought to, once you converge, you ought to see a shape of the glacier which conserves mass where there's a layer, and where there's not a layer, there was enough negative surface mass balance to kill off the glacier. So now for a little bit of numerics, because what I'm really now describing is a proof of concept calculation. It's sort of large scale, but it's still a proof of concept. There's no reason to believe this object is symmetric, so one shouldn't try hard to maintain symmetry like Galerkin, and instead a reasonable way, also because I was interested in the history of a certain finite difference scheme, is to think of this as an FVE method. If you're not familiar with this, basically it's an attempt to get the benefits of having a unknown represented as a function everywhere, and a conservation statement as your weak form. So I have my thickness living in a finite element space, and there's my weak form. It's not multiplied by a test function integrate. Of course it is multiplied by a test function integrate if you wish it to be. That is to say, you can have a control volume, and you can use your sort of Petrov-Galerkin. You can have a characteristic function of your control volume as your test functions. But when you do that, my original interest, what got me started on this entire thing was actually this slide, which is trying to figure out how an old finite difference scheme could be a finite element scheme. And I sort of succeeded in that very small task and realized, aha, I can fix it up, and indeed it helps a lot. Moving quadrature points makes things work, whereas the old Mahaffey scheme doesn't allow much Newton convergence. Also, there's an upwinding issue, which is too technical here. Okay, but from now on, I'm going to do two things. One is to restrict to the steady case. I think I did that on the previous slide. And the other is, now this is a big simplification, there's my momentum solver, okay? So that is to say, I'm talking about a momentum solver which is sort of trivial in the sense that you can work within any column and get the velocity and thus this horizontal flux. So that's now what I'm actually going to talk about. Even that is, in my experience, tough to solve. So here's an ad hoc continuation scheme on top of it. That is to say, start with a classical obstacle problem using your climate, using your bed for your glacier, and a sort of pseudo-diffusivity, which comes from vertically integrated viscosity, essentially. Solve that problem, try to get quadratic convergence, and then run with less and less regularized until you have the unregularized problem. That's the goal. And I would say, at this point, I can claim some success. There's a paper that came out on Friday. I can send you a copy if you want, and it has this picture in it. This is a reasonably large scale for a NCP problem. Shallow ice approximation, mass conservation, nonlinear complementarity problem. Sorry, steady. And the problem is this: it's given the data, just find the shape of the Greenland ice sheet. That is to say, no time stepping. And in fact, this and the paper I wrote with Guillaume in 2012 are the two papers that ever do this. Nobody had done the steady problem. The time stepping problem had been done for ages, and there are lots of calculations, but the steady problem is essentially a new one because it's constrained. Here you see the mountain ranges underneath Greenland, and there you see ice. And at least in theory, we all believe this is a well-posed problem. There's some evidence that it's well-posed. But in any case, it seems to be well-posed when you solve it numerically. It just seems to be really rough. And the essential difficulty is something that's happened. I got started on this field only recently in 2005. But since then, NASA has flown 50,000 hours of P3 Orion flights with ice-penetrating radar. Over much of Greenland, and the bed has gotten a lot rougher, okay? And it makes all the difference in convergence. That is to say, if you just use on the same resolution of grid the old data, what I described works great, okay? But the fact of the matter is that's not really respecting the data, because we don't believe that the bedrock underneath Greenland is this krieged, smooth surface that it used to be in the data that went into this problem. It's now better data, and in fact there's a huge uncertainty quantification issue about this, and it really makes a difference to convergence. And basically this is for the steady problem. You can fix, my only way to make it actually converge is to do some time stepping, 100-year time steps, long time steps, but they're easier than the steady problem. So that's it, and I'm hoping I'm doing okay on time.
Yeah, you're all right.
Okay. Okay, so my problem, my claim is fairly generic actually, although glaciers and ice sheets have this very strongly signed climate. It's a climate that is so negative sometimes that, as now, Canada has no ice sheet, and so positive other times that all of Canada is an ice sheet, okay? So this is a problem where you really have to pay attention to that term, and if you've seen somebody talk about tsunamis, they solve the same equation in a totally different context. They have some of the same issues, interestingly, but not, I agree, not quite the issues here of this really strongly signed climate. Anyway, if you have a signed climate, the thickness being non-negative has to be part of the problem, I think. And it certainly has to be as a practical matter if you want to take long time steps. And I should say maybe the reason I want to take long time steps is I want to, for ice sheets, we have yet to see the equivalent of weather for an hour. Ice sheets in the observational era, the last 30 years of satellites, have barely moved. If you want to see what an ice sheet really does, you have to go back in the last few ice age cycles and look at data that actually does exist, but that is to say, moraines and dated moraines and rocks get exposed and start being exposed to cosmic rays. There's a lot of data about where the ice sheets were. It's all geometric. We don't know what the velocities of these ice sheets in the past were. So to use that data, you have to have models that you can somehow invert in this temporal sense. That is to say, you have to have a model that can really do high resolution, long time scale runs, which presumably means not having the minutes and hours time step restrictions we currently do on sub-kilometer ice sheet time stepping models with their explicit update of geometry. Anyway, this is my advertisement. If you want to get into a field which sounds challenging, this is my attempt to make this one sound challenging. How's that? That's why I put up the red. So, thank you.